this. Okay, hi everyone. Welcome to this last part of our school, and I hope that you will come numerous to the conference part, which is tomorrow. And today I cheated a bit, so I will not speak about challenges. I will speak only about one challenge that we are facing, and what we are facing is the optimization of the setups, and this is actually a quite common thing for both industry or industrial applications of data analysis or scientific application. And normally this is a question of I say survival. So we need lower the cost as much as possible in order to have better setup and to have a better efficiency. By lowering the cost, I mean lowering the financial costs, or for example, having less emissions, or making a faster production, more samples in one term or something like this. And we probably need some kind of digital twin of the setup for a better tuning. So when we speak about having some kind of digital twin of what we want to tune or what we want to describe, we normally come back to surrogate modeling. And generally, there are several types of surrogate modeling that are available, and here we can actually come to surrogate modeling as a part as a different approach. So we can have something like local models that only describe a very brief part of the system, or a very small part of the system, or we can have some kind of full simulation like shown in the graph here on the right hand side. And actually I can point here, probably. No, the pointer doesn't work as well. Okay. And the last part of the surrogate modeling, which normally is avoided in our view, so this is the experiment. Actually, we can have an experiment which provides us with some kind of understanding of the system under study. The problem here is that we need to have a model which is somehow can have some kind of computational possibilities, which is data driven. So it should describe something about the real system we are speaking about, and we need to actually achieve some goals, like for example design optimization, or like configuration space approximation, or something like this. And generally this is needed, and we need to have it in order to have model management. So there are lots of places where we need this kind of approach. I mean, we have something like drug design, or like aircraft engineering, or steel production, or weather forecasting. Everything there requires some kind of surrogate modeling. But the problem is that if we use a very complicated surrogate model, we actually have very expensive calculations normally. And generally, if we are speaking about real systems, we speak about large parameter space, which we need somehow to explore. And for sure, we have some kind of numerical noise or uncertainty, which is coming from the fact that we don't have a very precise description of the system. So the question that should arrive is what we do when we perform this kind of surrogate modeling. So we need to create like initial sampling plan, which can be, I don't know, Latin cubes or anything, and then we start from the evaluation of the results of our performance. We construct a surrogate based on our evaluation on our first sampling plan, then optimize surrogate, optimize design using surrogate, and then add new design. And so we do it in circle until we find a good solution. So the question is how to construct a surrogate, and what if the surrogate needs quite a lot of intensive resources. So generically, there are lots of approaches. for surrogate modeling, we can have like, I don't know, we have polynomials that describe the response of the systems, or for example, neural networks can be used for surrogate modeling, or we can use Gaussian processes, and this is actually what we will use in some slides afterwards. And this is some kind of generic part of the optimization. And now we, as I promised, I will talk about particle physics and how we use this kind of generic things for particle physics detectors. And we start now from everyone that knows about it is the collider. Collider is a big setup, actually the biggest setup the biggest experimental physics setup that was created on our planet, and this is it's as big as as the Geneva airport. So Geneva airport is on the right of the picture, and the circle is the collider. It's called large. I mean, because it's large, and hadron because this is a type of particles that are actually inside this collider. So there are millions of events per second, and there are lots of underlying models that are governing the collision outcome. And we need like hypothesis testing for theories that describe models, and so we need some kind of new models that are tested every time that we start the collider, and we run the collider now. And one of the famous things is the Higgs boson, which was discovered 10 years ago now in this collider. And actually, this was discovered with this kind of experimental setup, which is located very much underground. So 100 meters underground, and the experimental setup is some kind of cameras, and that has got many layers of sensors, like 200 square meters of matrices. The resolution of these cameras is around 100 megapixels. The photo speed is, well, it's a bit less than photo speed. So it's 40 million events per second that we need to have a photo of. However, we are able to record only 200 or 1,000 or up to 1,000 photos per second. So we need a very aggressive selection of the photos we need to record. And we work for many years, so we have a lot of data. But what does it look like? It looks like this. So this man in the yellow t-shirt is not me. And in fact, the detector looks like this. It really looks like a camera. It's a part of the detector. So it's constructed out of many parts, many small parts, which look like they're on the right-hand side of the slide. And in fact, you can see that it's very expensive to construct. We need to have a small amount of we need to spend as small amount of money as possible in order to have the best results out of this detector. That's why we need to use some kind of smart approach to optimize these detectors. So let's go to tuning of the experimental setup. So first of all, as I told you, we need to construct a theory. So on the left-hand side, we have particles collisions. This is something which is seen in the collider. And on the right-hand side is just one of the equations of standard model of particle physics. So we need to pass from this part to this part. So what we do, we have to collect the data using the detector or the camera, which I showed you before, and there was a photo of one of the layers of the detector. And in fact, the event looks like this. So this is a projection of the event that is collected by the camera, and you see this is the representation of data that we have. This representation should be analyzed in physics way, and in fact, so before inventing of the large-scale computers, it was analyzed using ruler and pen and pencil. Now we use computers, and the computers out of this amount of events, we look for good particles, and we actually reconstruct the exact physical parameters of the particles that are created inside the collision. Then we go to theorists, and theorists say, okay, but this is evident. This equation is describing everything that is created in the collider. So now this is what we have, and now we have government. The government gives us money. So the government actually doesn't want to give us money, as usual, and they want us to have a small amount of to spend a small amount of rubles or Swiss francs, and to have and to actually discover something for the smallest amount of money possible, and for the smallest time possible. So what we can do, we can try to understand how to tune our detector, our analysis, in order to create the best possible configuration for the detector, and so that the theorist can actually discover something very fast. So what we do, we need to understand what we measure. We measure something that is property of the particles that are created inside the collider, and these properties are somehow measured using two steps: is data collection and data reconstruction. So what we want to have is to understand how what is inside the event. So we have physics, which is real physics, and they have got the physics has got parameters like p, for example, let's say. Then we have a detector that is running and trying to extract what is happening inside the collider, and the detector has got also its own parameters, theta. The detector, unfortunately or fortunately, works in real life, and real life means that it has got some stochastic processing, so particles go through the detector, and it actually can interact or not interact with matter, so there is some kind of stochastic parts. Afterwards, we go through reconstruction, and there is an algorithm which has got nu as a parameter of reconstruction. And finally, we measure something which should look like physics parameter p, but it has got p bar, which is just to show that we measure, and it actually depends on what we have as a stochastic and detector and algorithm. So it has got some parameters inside. So our goal is to have something which is as close to physics as possible. So in this case, we will have the best measurement possible. This is more or less easily done if we have enough money, but we need to actually have to limit ourselves to have a small amount of money, and so we normally go to government, and government says, okay, so we have this amount of money, and you cannot go very much higher than this. We need to spend, but it's better that we spend lower amount. And what happens? We need to choose the correct detector configuration and to make it automatically. So that's why instead of data collection here, we can use simulation. So some kind of twin of the detector if we know some processes that are happening inside the collider. And since we do it for 100 years already with particle physics, so we know some things that are happening there. There are some problems. The problem is that we have this simulation, and we have to have simulation that represents what is happening with physics inside the detector. So it's a kind of stochastic process which is happening there. And normally to describe this, we use a physics-based simulation, which creates one event per minute. And I remind you that we had to record around 1,000 events per second. So it's quite a different amount of events. Then the problem is that we have an algorithm which is chosen manually, and in the end, what we have is overall goal, which depends on basically on money and on the amount of uncertainty that we have while measuring some physics quantity, and this part is not differentiable because we have some kind of part which is stochastic inside. So we need to understand how to deal with this. So we need to solve several problems, and here we have machine learning that helps us. And first problem, which is generally called the forward problem, and this is a problem that when we need to describe what is happening inside a detector based on the physics characteristics of the event that we look at. And in fact, we have very good simulations, physics-based simulation that I told you, but this is very complicated. This is just not to understand, but to show you that there are lots of very careful steps that we need to go through in order to have a real understanding of what is happening inside the detector. So we need to take into account collision, what is happening, decay of the particle, then the matter interaction, and then reconstruction. So each event takes around 1 minute to generate, as I told you before, and the real-world data is generated at around several megahertz before reconstruction and around kilohertz after reconstruction. So the idea is to simulate the simulation using effective parameterization. So let's look at what is an event. I told you that our detector looks like cameras, and this is actually how the photo of this camera looks like if you take care of only one particle. So this is the detector. This is the part of the detector, and in this part of the detector, the incoming particle will look like this, like on the bottom of the slide. And you see, it looks like photo in a way. And we need to just to understand how to recreate the photo based on our knowledge of what is happening inside the collider. What we can do, we can run the real physics simulation, but this is quite complicated and this is quite long to actually run. The second idea is to parameterize this event using some kind of effective parameterization. How is done? You normally take like 10 students and you give the students the same task, and one of the students will actually create something good. And the other part will be to use some kind of generative modeling, and the generative modeling actually create you a picture that looks like a picture created by detailed simulation. The only thing that we don't know physics. So we use generative adversarial networks in order to create best description possible. So we have some kind of conditional representation of what is happening inside the detector, and this creates a conditional dependence on the parameters of the detector theta and the incidence particle information p. So, and on the right you see the figures. On the top there is a figure of what a real life particle looks like. On the bottom row you can see a figure of what was imagined by the generative adversarial network. So this looks more or less very close. The only thing is that it's a bit different, and it's normal because of possible internal fluctuations inside the detector. So again, on the top it was created using some physics knowledge. On the bottom, this is created by a generative adversarial network that doesn't know physics for sure. And this is something new. However, it actually created a lot of movement inside the community of particle physicists. So I think starting from around 2018, this is our paper 2019 so for the pictures, but the first results were from 2018 from the data detector, and actually there are lots of people that were trying to understand how to use generative modeling, YE, or generative adversarial networks, or normalizing flows, not diffusion models, for a moment at least. And they understood that actually generative modeling is the best part to create good simulation of what is happening with the matter. So because it's the simulation is actually tunable, robust, and fast for sampling. So the main thing is fast for sampling because I told you we need to be very fast. This created actually quite a lot of challenges. So we are currently working, so we have several challenges before us, and so we are working now on the distilling the generators. So currently we are able to describe fully what is happening inside the event, inside the detector, with the help of generative adversarial network, and we only waste around 200 milliseconds, but we need to go beyond 100 milliseconds with the same quality. So we need to create the testing of the generation quality in the limit of small data samples, because we need to understand very fast what is happening inside the detector, and we aim to have on-the-fly algorithms, and for sure implementing the pipeline, and this is an idea of the pipeline that we use for Joint Institution of Nuclear Research in Dubna. The configuration is not the same, so it's using some configuration of the cluster for training guns. So currently, for example, in CERN there is like a cluster of 200 A5000, and we need to have efficient architecture for scheduling the resources and for saving the models. So this is actually the challenges for the forward throw problem. For inverse problem is actually a bit easier. So the inverse problem is something that is based on the detector response, creates a measurement of the physics properties of the particle. The inverse problem is, I will not go into details, it's actually evident that we are able to train neural networks to to reconstruct the incident particle properties. The only challenge here is to make it quite robust and robust enough, and this challenge is actually understudy in many places. So the current solution is that the reconstruction is self-trained for every point of the detector configuration, and we will have to switch to universal training for all the points of the configuration of the detector. So what happened here? So we have a big optimization. So one part of the optimization is actually covered using machine learning, using generative adversarial networks, and this is a part which is a stochastic part. Then algorithms are actually also done using algorithms of reconstruction is actually covered also using machine learning, some deep neural networks. And now we have everything except that we don't have a real differentiable setup. So we need to create some kind of surrogate. And actually, what we have is a classical formulation of a black box optimization problem. So the value at any point is known. So we can, for example, have a setup, experimental setup, and we know what is the cost of this setup and what is the actual precision of this setup. The analytical formula is not known because we don't have any ideas of how the whole function looks like. We need a lot of time to compute the values, even with using generative adversarial networks as a simulator and deep neural networks as a reconstructor. And so we have some kind of optimization problem that is easy to address. Easy to find in the literature. Is not easy to address, unfortunately. And there are several places. There are several ideas how it can be solved. First of all, and this is a general idea how to solve this kind of problem, is the expert method. Basically, you invite an engineer, a senior engineer, and the senior engineer says, this is the best configuration, I think. And so afterwards, you create the best configuration according to senior engineer idea. And the problem is that it might be wrong. I mean, senior engineer can be, I don't know, drunk, or can be just wrong because of some kind of biases from the past. There is also something that works surprisingly well is a random search. So basically, you randomly search for configuration inside the big configuration space. You can try to randomly pick several points, or not randomly, but or smartly pick some random points, and you actually can create some kind of good configuration of the detector. And then the other part is surrogate modeling. So we used some kind of modeling like this, for example, in the experimental design in last years. And this experimental design was done in the following way. So we have a experimental setup, which is on the top of the slide, and we have an incident particle which is coming to this experimental setup. The problem is that we don't need this particle to give any kind of daughters inside the experimental setup. So we need to reduce the amount of radiation noise inside the experimental setup. So we need to measure nothing inside there. That's why we put very big magnets. And the magnets should somehow take out the experimental the particles out of the detector. So the particles under the magnetic field, they can behave like on the top, like they go up, and like on the bottom, they can have some kind of wavy parts. The problem is that they can also return back to the experimental setup, and this will create some kind of noise for our detector. This is a pure optimization problem because it has got like several tens of parameters, and we were able to actually create some kind of model that is responsible for the calculation of the amount of particles inside the experimental setup based on our understanding of the physics of the process. So this actually created based on our understanding of physics, we were able to use Bayesian optimization of Gaussian processes that based on the that created a surrogate modeling, and we optimized the detector from something that was a part of expert solution to something that was suggested by our optimization problem, and this actual optimization brought a 25% cheaper solution. So what happened here? So that we knew how the system behaves. We created some kind of loss that we described using Gaussian processes, and then we put additional points at the places where we wanted to have better information, and this actually created us a possibility to have a surrogate modeling using Gaussian process regression. And out of this, we were able to take out the better performance detector. The 25% cheaper solution actually gives us like 1 million million Swiss francs, and this is quite encouraging for financial parts of the science. And so we are able to run, although quite complicated, we are able to run optimization that is finding the best solution for engineers, and we are able to find the most efficient solution based on our understanding of physics results. So the challenge is actually the following. So we need optimization of the large setup that is requiring quite a lot of computing power. And the problem is that this computing power is somehow situated inside the physics-based modeling. We used machine learning, for example, generative adversarial networks or basically deep neural networks in order to create some kind of understanding of how the system will react to our problem. Then in the last part, we created some kind of surrogate modeling. This allowed us to have a complete optimization cycle, which is automatized, and we are able to have better results. I mean, less expensive results and more efficient detectors on with the same amount of money. And so many areas actually now are being re-explored using this kind of approaches. So on this or that approaches. So among them, like I don't know, tomography, like medical imaging, like astrophysics setup, and other areas. There are many areas that are re-explored. You can go to this collaboration to see the recent talks and to see what are the approaches that are basically used. And we keep on trying to solve this challenge to actually create the best scientific performance given the amount of money that we have for the science. All right, thank you. Yes.
Can you please go to the slide 36?
36.
Yes.
Yes.
So we have parameters theta, and as far as understood, you may change the geometry of the detector significantly. Yes. So how do you estimate that if you change the geometry, your generative models produce reliable detector readings?
Yes, thank you. It's actually a very good question because we are also working on this. So it's a question of conditional robustness of generative adversarial network. Conditional robustness of generative adversarial network. The idea is the following. So you have good description of the detector for one type of parameters, for one set of parameters, and for another set of parameters. What is happening inside between them? What if we have interpolation? The answer is the following. So we have several tests, and we are able to, if the points are close enough, what is close enough is it's very hard to tell, but there are some ideas. If the points are close enough, then we have a very robust interpolation. If the points are a bit farther away, then the interpolation can be very, very bad. And this is due to the fact that generative adversarial networks are very expressive. And also depending on the conditional on the conditional of GAN. And what we try to do is to create some kind of some kind of regularization based on on the closest on the, let's say, on the distance to the closest parameter set which is known, and this regularization will should be able to kill the expressiveness of GANs in this part, and so we will be able to have more intuitive, let's say, interpolation between the points that we know. For sure, extrapolation is much worse. So we will have to limit the ourselves inside the places where we have some kind of knowledge. For extrapolation, it will work like this. So you want to go somewhere outside of the box, outside of known parameters of the system. So what you do, you simulate, you have a real simulation or real experiment somewhere, not very far away, and then you try to explore using generative adversarial network, try to explore the place between this new part and the known part, and so you interpolate like this. This is actually something that should be done. I think it will. I mean, ideal system, which I bet will be somehow developed in like 5-6 years from now. Ideal system will do this.
So, for instance, to make a single gun, how many simulations, hardware simulations, at different points you should have?
All right. So we. Okay, so for one point, so for detector, for HTB detector, for big detector, for one point we need like around 100,000 of events. For several points, for several configuration sets, okay, so it depends on how much you want to interpolate. So generally, if we try to interpolate very far away points, and they failed. So currently we are working on the metrics to understand what is the close parameter sets.
Okay, thank you.
Okay, thank you. Not. Different surrounding, right? So it's not cool, this conference.